Okay, thank you everyone for your patience. We start now with the second talk of today, and this speaker, I guess everyone knows because he is also the main organizer of the whole seminar series, but anyway, I will introduce him. Pavan Pranjivan Mehta is currently a PhD student within the mathematics area of SISSA, Italy. He holds 2 master's degrees, one in thermal and fluid engineering from the University of Manchester and one in applied maths from Brown University, with an undergrad in aeronautical engineering. He has held research positions in France, the USA, the UK, and India, with an internship at Airbus Group, and has been a visiting researcher at the Isaac Newton Institute in Cambridge for 2 scientific programs, namely Turbulence and Fractional Differential Equations. Pavan's organizational activities for fractional calculus include mini symposia, prestigious conferences, and seminar series, such as JINX seminars at the Isaac Newton Institute and weekly seminars at SISSA. His current research interests are non-local turbulence modeling and numerical methods for fractional PDEs. We're happy to hear from him today about fractional Navier-Stokes equations. Pavan, the floor is yours.
Thank you very much, Arran, for the kind introduction. It's really a great pleasure to talk about fractional calculus and turbulence. The two topics are one of my favorites too. So in this talk, I'll be first developing the vector calculus, then that will be the machinery for deriving the conservational laws for obtaining fractional Navier-Stokes equation from first principles. So let me motivate the fact that why did I got interested in the first place. So my previous work was on Reynolds-averaged Navier-Stokes equation. So now the Reynolds-averaged Navier-Stokes equation are nothing but time averaging the Navier-Stokes equation you obtain the Arran's equation. And the reason we like this equation a bit because solving the Navier-Stokes equation is too computationally expensive to the point that we cannot solve anything of industrial importance in the biggest of the biggest supercomputers. So we look for time average velocities and pressure but therein lies a problem in solving this equation, which is number one on the slide. That the moment once you time average this equation from the non-linear term, you get an additional term which is the little ui and a little uj. This is called the Reynolds stresses in the honor of Osborne Reynolds, who primarily derived this equation. Although it's an exact equation, but the question remains, like, how do we obtain this term? So since 1972 or 1974, one of the first paper on K epsilon model came into picture, starting from the idea of Prandtl. Which showed that it is possible to have some simplified assumptions and assumption to develop more equations, but these are not from first principles, but rather than ingenuity of people around. And the moment you go to another setting, the model may or may not work. And for this very reason, turbulence modeling is still quite an active area. So we looked into this problem as well. I have to mention that that Professor George Kanadakis actually had the idea that probably we can introduce fractional calculus for to solve this closure problem. And ever since I've been working on this topic. So then I came up with it. Came up with this hypothesis that the perhaps the total stress, which is the term in the brackets can be written as the stress can be written as fractional strain. And this hypothesis actually worked very well. We had like really nice physical results for complicated settings too. But one of the issue was that to capture the entirety of 3D flows, one needs 9 fractional orders to do that, and these fractional orders are also variable orders dependent on space and time, so that's pretty complicated to do that, and we still don't have the enough equations to close this problem. So I wasn't very happy about it. We just translated the problem from finding Reynolds stresses to finding fractional orders, and I was not of the opinion that that we should go in a classical direction where we go to another setting and assume that all right, what is the fractional order should look like in here, and move, and of course, if you go to a different setting, that that may or may not work depending upon the assumptions that you have. So the overwhelming question remained to me is like, probably I should derive it from first principles, and this has been a question that I'm asking myself from the last 2 to 3 years, and I finally had the realization that I could actually do it by way of vector calculus, uh, calculus, and for that, I will not I will extend the Tarasov's calculus, which was developed in 2008 in a paper published to two-sided operator. The reason I do this is because what I understand from physics, what does a gradient operator should look like. Tarasov had a very similar extension to higher dimension, and and what does the gradient operator should look like in his case too. But in his paper he had results for one-sided operators, so I had to extend it to two-sided operators, because physics demands that it needs to be a two-sided operator, just not a one-sided operator. So we look into the fundamental theorem of calculus, and the fundamental theorems, second fundamental theorem 7 will be the key, will be the key result to extend it. Now notice that these are two-sided fractional integrals and two-sided fractional derivatives of Caputo, with the order which is a variable, but for simplicity, I'm not denoting it as a function, just as an order. Now notice that when you do this, you actually have 4 terms, and the two of the mixed terms do not actually cancel out. So I had the idea that probably I can use the indicator function for function and make them make the terms that the mixed term go to 0 by the choice of the indicator function, and thereby the 7 holds, and this is not a very strong a strong assumption of adding the indicator function. In fact, uh, uh, as we progress in it, you will start realizing that this is even more physical to do it. So having defined the two-sided operators, let me talk about how does one extend the define the gradient operator. Now it can be done more or less classically, where you have a partial derivative in the x, y, and z direction. But in this case, these are two-sided fractional derivatives, And one thing, notice that in equation 9 you have alpha, beta, and gamma. So the alpha is associated with non-locality in the x direction, and beta is associated with the non-locality in the y direction, and subsequently gamma is associated with the non-locality in the z direction. And all of these order of the operators are variable order dependent upon space. So if your space is three-dimensional, then it will be x, y, and z. So it is a scalar field, say scalar field. And once we have this gradient operator defined, it is very trivial for me to define the fractional divergence, where one takes the dot product of the function and the and the gradient operator. My notations are a little all over the place, so I apologize, because I was working on different notations for different things, but I'll try to do so. So from here onwards, I'll use this notation to denote the two-sided fractional derivative. So having defined the gradient operator, let me talk about integral operators. So think of so let's see how can I extend my line my fractional line integral. Now to take the picture, and consider the top and the bottom, and the bottom line segments. Now, now the question I want to ask is how should I define which domain I should define the left and the right. So, for example, if I fix in the bottom line segment a left and a right, should the top be the same, or should it be reversed, because I want to go in anti-clockwise to clockwise. So the answer lies in considering that what if this element actually collapses and delta y goes to 0. So if it was done in an opposite way, then you have inconsistency. So the left will the left will the left becomes the right, and it collapses on the right. So that's not very natural. So this is this is how one needs to define the left and the right operator. And once having defined the domains of the integration, and you can take you can go and you can go in an anti-clockwise sense to define the line integral. So basically it will be a left integral here, a right integral here, left here, right here, and so on and so on. So once I have a line integral, let me extend it to a surface integral. So the surface integral will have the x variation and the y variation. So the x variation will have two terms in here. So is the y integrals will have two integrals. As a result of this definition, now I have four terms. So it is very evident. It can be trivially seen that in this diagram that there are four regions as well. So having defined this surface integral, the volume integral follows a similar idea. So I shall not show it right now. So let me talk about the Gauss divergence theorem, and this is a theorem that's gonna be the central role for us to deriving the conservational laws. I'm denoting my surface integral as this, and from here onwards, and the volume integral by this, where kx ky are the kernels, at the kernel in the x, y, and z direction as a function of space, not in time. And this will be a bit important to know that. This indicator function is not by the virtue of the definition. It's just that I'm combining it from a to x, x to b to a to b. A to B. So this indicator function has very little role to play in any of this definition. So now have we defined the Gauss divergence theorem? So let me talk about the fractional analog of the Reynolds transport theorem. Now the Reynolds transport theorem classic is the central idea how do we derive the conservational laws. So this is the central tool that will be using it. So let me extend it to its fractional analog. So equation 17 is something that what is classically considered, and the fractional analog will be, of course, 18, where you have a fractional volume integral associated with a fractional time derivative. Note that the fractional time derivative is a left-sided operator, while the fractional operators in space are two-sided operators. Uh, uh, so our strategy for deriving this is going to be very simple, where we're going to take the integer order time derivative of it, of the fractional volume integral, and then once we have the result, we just commute the fractional integral to get the fractional to get the fractional time derivative. Uh, so so the idea is follows the same strategy as the classical case, or in the case of Leibniz as well, where you have a function and you do a Taylor series expansion, or expansion of it, and you have a series of term. One of these cancels out the other at the limit delta t tends to 0 goes to 0, and the other term, one of the other term, where the volume integral is on a delta v, which is the small volume. Now that can be at the limit delta v goes to 0. That volume integral can be approximated as a surface integral, and once you have the surface integral, and you plug that part in this equation, and take the limit to get the get the fractional transport theorem. Once we have this equation 24, you just take the fractional integral of order 1 minus zeta to get to the final to get to the final form. So now we have all the tools that we need. We have the divergence theorem, and as well as fractional Reynolds transport theorem to derive the conservational laws. So we'll dive into it. So this is one of the first equations one considers is the conservation of mass. Now, in case of equation 26, you have a volume which is a material volume. A material volume implies that you start with some fluid elements, fluid elements, and they may go and in certain time they may travel in space, and travel in space, but such that the equation 26 holds. For equation 26 to hold one thing one needs to realize that the boundaries of this material volume is not going to be fixed, but it will keep changing it. You may think of this as some kind of a balloon. Balloon, I mean, the mass inside the balloon remains fixed. Now let me consider the fractional analog of it, which is equation 26. Now the question I want to ask is, why would that be equal to 0? For that, let me motivate the fact that when do I have to take when I have to consider the non-local terms explicitly. So, so realize this in this setting, we are no longer working on infinitesimally small elements. We are talking about big elements, which can be either coarse-grained or coarse-grained, or there's just simply big elements. The underlining thing here is that the information of all the scales or the trajectory is missing, and in order to address that question, a non-local operator naturally emerges. Uh, so but the physics behind is the same. So if you have a big element, and if the little element follows 26, implies that is zero. If I take a sum of all these little elements within my big element, it would be zero as well. It's basically addition of zeros. So the zero on the right hand side of 27 makes sense. Once now I can invoke the fractional Reynolds transport theorem to 27 to get to the point that I have equation 28 to 28, and that surface integral which I have in 28, I could then use the Gauss divergence theorem to derive the final equation, which is equation 30 on my slides. Now note that the time is integer order, which is actually quite surprising to me. I thought time would make it come out to be fractional order as well. I was expecting a fractional order in space, which is a direct consequence of the fractional Gauss divergence theorem. One can further simplify it in the case of incompressible flow. In the classical setting, it's the divergence of the velocity is zero. But in this case, for this big element, or when you understand u as a coarse-grained variable in space or time, it will be the fractional divergence of the velocity is zero. Now, now we look into conservation of linear momentum, and that's what we call the Cauchy equations as well, which not only applies to fluids, but it also applies to pretty much every continuum mechanics with a suitable stress tensor. So the starting point of the conservation of linear momentum is the Newton's second law. Second law. When you have a fluid and not a rigid body, an integral naturally appears to it. And since we are not talking about smaller infinitesimally small elements, but we are talking about coarse-grained elements or bigger size elements, a fractional term emerges. Now I can do my same trick of using Reynolds transport theorem on the left hand side of 32, and then subsequently I use my Gauss divergence the theorem to make all the surface integrals to volume integral to get to the final equation of 35, which is the fractional Cauchy equation written in index notation. Notation. So now the question here is the question here is, what is this this term TTIJ? This is nothing but the but a stress term. But in the for different continuum mechanics, you will have the different stress term. So the equation 32, which is the fractional Cauchy equation, which is very much general. But we are interested in fluids, so we'll try to motivate the fact that how I can obtain the stress tensor, in here. Now, the arguments more or less are very much classical from here, but for the sake of completeness, for the sake of completeness, one can consider that the fluid at rest the only forces that will be acting will be from the pressure, from the pressure, and once if the fluid is not rest, in addition to the pressure, you also have you also have a stress term arising from the motion of the fluid itself. Now look at equation 39. This is a second order tensor, and this is another second order tensor. To map this second order tensor to another second order tensor, you need a fourth order tensor, for fourth order tensor, and the second order tensor is nothing but the symmetric part which is related to deformation. And why this, and not the tensor that is associated with rotation? Well, if the fluid rotates, it does not it does not it does not create any stress. Stress is prime by definition. Stress comes into picture once you have some kind of a deformation of the fluid element. So hence the term Sij. In its full generality, this fourth order tensor has 81 terms, but we are going to try to motivate the fact that the fluid that we are considering is an isotropic medium. Isotropic medium. So this fourth order tensor has to be can be written as a second order tensor, and equation 41 is by far the only combination that you can have here. Now lambda, mu, and gamma over there depends upon the local thermodynamic property. And these arguments here are actually very much classical. With the only with the only difference is that instead of having a strain tensor which was integer order, now we have a fractional strain tensor, and this was this was a well established, well studied topic in my previous paper, and the hypothesis I had it in the beginning where the stress can be related to the fractional strain. So all of these arguments are more or less classical, and this leads to me the final form on 51 for okay. Okay, so once I plug 51 into the fractional Cauchy equations, I get my fractional Navier-Stokes fractional Navier-Stokes equation. One can further interpret this term, this term as a fractional material derivative. So think of this of this. If you had integer order operator, then this is nothing but the material derivative. And similar to the Caputo definition, instead of taking d by dt d by dt term in this bracket. Now I take the fractional for fractional material derivative defined in space to get to the final full generality of fractional of fractional space and time material derivative. But this is just a definition. Equation 52 is the fractional Navier-Stokes equation. Now, let me take some cases, some case studies and see that this is the equations that I have has some any merit or not. Now realize this, that the equations that we have developed in 55 and previously for the conservation of mass as fractional derivative does fractional dimensions as well. And this equation is actually imbalanced. So the dimensions on the right do not correspond to the dimensions exactly the dimensions on the left. And so far been my exposure into physics, mostly Newtonian physics, physics of continuum mechanics. This is not very natural to have dimensions to be imbalanced. So it was very natural for me to obtain the non-dimensional form, but to non-dimensional form. So I just introduced yeah so solve for a variable which I call it as u plus x plus and p plus p plus. Now I strongly advocate that non-dimensionalization has to be the way to go forward if you're not happy with dimensions being imbalanced, as opposed to the fact that you add an arbitrary coefficient or a term to match your dimensions on the left and the right. Now because what happens is that then you'll be left to interpret what is this arbitrary term of fractional order, probably fractional viscosity or something, but in nature it may or may not exist. It's purely artificial. So it may very well fail. So what you have is a derived equation from first principles, and if you add an arbitrary term to make the dimensions nice enough, to nice enough, uh, uh, this nice equation will start will lead to solutions that may or may not exist. So I strongly advocate that non-dimensionalization is the better way to proceed rather than adding such arbitrary coefficients. Now, so now let me take the example here. Now let me do one thing here is that let me ask this question: what is what is the velocity and pressure in that Arran's equation, in that fractional Navier-Stokes equation? I did mention earlier that this can also be interpreted as a coarse grain variable. A coarse grain variable in time is not is the variable that appears in the Arran's equation, which is the Reynolds-averaged Navier-Stokes equation. So let me plug in the time average velocity velocity and pressure into the into the into the equation and see what I get. So I'll do some case studies on the channel flow and the Couette flow. For Couette flow, for the channel flow, the walls, walls are at rest, and the flow is driven by the pressure gradient. Uh, uh, the other two directions are purely homogeneous, and all and anisotropy only exists in the y direction. And since this is a mean variable, the time the time term vanishes and it reduces to equation 60. Uh, let me check how can I obtain this fractional orders given the velocity. Given the velocity, for that, let me take the left integral for the left fractional integral for this for that equation to and use the fact that at the center line for the specific case, this term is zero to obtain pressure gradient term. If I solve 65, I get an anti-symmetric symmetric fractional order, but this flow in here is very much symmetric. So to obtain a symmetric fractional order, I started by taking left-hand fractional. I'll also take the right fractional integral and proceed towards similar arguments, and finally I'll add them together to obtain my final equation. Now let me also take the case of the Couette. For the Couette flow, one of the boundary is at rest, and the other one is moving at a constant velocity, and the pressure gradient is zero. The arguments, more or less, the rest of the arguments follow the same as the channel. It's a channel, so this reduces to equation 67. I'll do the same thing where I take the left and the right fraction integral, and then I'll add those two equations together. Now, equation 71 was also baffling to me, because this is the exact equation what I had it in my previous paper when I was talking about Reynolds-averaged Navier-Stokes equation. This two was on the other was on the other side. Was on the other side. That was not that was not a derived equation, but rather I just had a very good intuition, like of how to proceed. So naturally, if the equation is the same and same, the fractional order will be the same as well. But for the case of the channel, this equation, the right hand side is very much different what I had it from my previous exercise. But to my surprise, the fractional orders, starting from the fractional Navier-Stokes equation and the fractional orders of the Arran's equation are exactly on top of each other. This was a very surprising result from me, because the starting point of these two these two equations is very much different, and if I understand the velocity as time average velocity, which I have it from Arran's equation, and plug it into Navier-Stokes equation, which I'm allowed to do that because I'm talking about post-grain dynamics as well. And the two fractional orders and everything is exactly the same. Now let me remind you the starting point for the Arran's equation is Navier-Stokes equation, integer order, followed by time averaging it. Then we introduce the fractional hypothesis to get to that point, to get correct. So it's totally different, like starting point. But I'm very happy to see that the fractional orders are on top of each other. Naturally, for the Couette, the equation was the same, so there is no point in solving it. It's going to be exactly the same fractional order. So since the fractional order are the same, let me talk a little bit more about the results results and conclusions from my previous paper, which is Mehta 2023. So this is a very physical result. So around here, what you have is the viscous sublayer. This is where you have molecular diffusion and no turbulence at all. So in that case, the fractional order is, or what I get is, corresponds to a standard diffusion operator. And I slowly, if I slowly move towards the center line, this is where the turbulence intensity is the highest. The fractional order decreases corresponding to the to the intensity of turbulence, turbulence, and there is a region in between around here where you have both molecular diffusion as well as turbulent diffusion. So this was very much physical. So let me study this fraction or orders a little bit more. So if I have to plot my fractional orders for different Reynolds number, depending for my half channel width, what I see that there is some kind of a very nice universal scaling, and followed by followed by some weak behavior in here. So it is possible for me to write it as the fractional order as a universal part and the weak part. Now this is something which is also classically done for the case of velocity as well, as well. And that is what we call the law of wake for the case of velocity. So but for the case of fractional orders, I also have a similar scaling. If I somehow if I find it took me a while to find this expression, but if I subtract to it, you can clearly see the universal curve. And let me do a bit more study on that universal curve. Now I want to understand that at the limit of Reynolds number to the power goes to infinity, will this fractional order asymptote, or there will not be any solution. So what I'm going to do is compute the minimal fractional order, since they all fall in the same curve for every Reynolds number, and plot the minimum alpha correspondingly. So in this exercise, I did it I did it for a very for extremely high Reynolds number. I did not have experimental data, but it was for the considered case, it is possible to generate synthetic data. So the value may not be the same, but conceptually speaking, I want to see whether the fractional order asymptotes or not. And and to my surprise, to my surprise, I was able to able to fit up a power law curve for both these cases. And one property of a power law curve is that the fractional is that it asymptotes. So if I take the limit Reynolds number to the power the Reynolds number to infinity, indeed the fractional order is going to asymptote, and it's going to be within the range, within the considered range. And so at infinite Reynolds number limit, this is going to have a physical solution. And I also took some time to find to find an expression for the fractional order. So 75 and 76 would actually correspond. 75 would correspond to for the case of the channel, the fractional order would correspond to it. So that those equation can give you can generate this for this fractional order. I obtained that equation purely by a very elaborate fitting exercise, and and the fractional orders from this expression are roughly gives you like 3 or 4%, 5-ish% max error, but the error is not uniform across the range. But okay. Okay, so let me summarize this talk today. So we extended the vector calculus which Tarasov developed for one-sided. I did it for two-sided operators. Then we obtained the analog of the fractional transport theorem by and following which we have the conservation of mass and conservation of momentum, which is conservation of mass is nothing but the continuity equation, and conservation of momentum as the fractional Navier-Stokes. And recall this if the flow is incompressible. So in the standard integer order Navier-Stokes equation, you have the divergence of the velocity to be 0. in this case, you have the fractional divergence of the velocity to be zero. And notice this, that the fractional orders are now actually coupled. So it's not only the velocity and the pressure that's coupled. It's the order that is coupled from this equation to the to the other equation. So these are this is three equations, and this is the fourth equation. For the fourth equation. So. And finally, when I considered the velocity and pressure as a Ran's variable, I was able to find those scaling laws because those are the fractional orders were exactly the same as my previous study. And to summarize that part, in the viscous sublayer, you have a universal scaling of the fractional order to be 1 because of molecular diffusion, and the buffer layer is the region where you have both molecular diffusion and as well as turbulent diffusion, or the diffusion very much significantly, both of them. So classically, for velocity, we don't really have any scaling law, but the fractional order is actually universal for this region. And in the in the classical sense, we have velocity that after the buffer layer we have a velocity scaling, which we call it the log law, because it for the considered case, it varies as the logarithmic of the distance from the wall. For that regime, we have a fractional order, which is a power law with different exponents, of course, and different constants for different cases. And finally, one talks about law of wake for the velocity. I can equally talk about law of wake for the fractional order as well, of a fractional order as well. These are the references. The paper by Tarasov is a very good read, and has the original ideas of how to extend it to higher dimensions, and he has subsequently developed the vector calculus for one-sided operators in this paper. This was our first paper, and this was this is where this is where we were very much motivated to look into it. Then subsequently, so subsequently I wrote another paper with two-sided operators, and then I also looked into tempered definitions, the definitions as well. And this current study that I'm presenting today is under preparation. I have to finish my manuscript, but first I fix my notation. So thank you very much for listening. If you have any questions, please let me know.
Thank you very much, Pavan, for the presentation. Does anyone have questions? You can unmute yourself or write in the chat or raise your hand in the meeting. I have a question from the theoretical side. These fractional gradient, fractional vector calculus operators, are they defined firstly by you?
Sorry?
Was it you who defined these operators, or are you using some pre-existing operators for fractional vector calculus?
Tarasov has the definition for one-sided, and for the two-sided case, I'm the one who came up with the definition.
Okay, very interesting. So nobody has done a two-sided fractional gradient before.
I highly doubt it, but the moment I had the realization, I mean, I just went all the way. I didn't even look into the literature. So if somebody has it, it may have it, but I really doubt it, given how given so many less papers are written on that subject. So yeah, yes, so this would be pretty much my work.
Okay, great. Yeah, there are a few different proposals in the literature for ways to do fractional vector calculus. Terrazos is one of them, but there are others as well. It's not something I've looked much into, but
Yeah, so Mark Meerschaert has an approach as well. So in his approach, what he does is that is that he does not consider what he considers is that instead of the primary variable f of x in here, what you can do is define a fractional vector field, and that and given the fractional vector field, you can use then you can use the integer order vector calculus to extend it to extend it. Now this is something I wasn't very happy about it, because the primary variable u exists in nature. There is there is nothing called as fractional velocity or fractional pressure. It's purely a mathematical construction. So I wasn't very happy about that, but that is my perspective. It may have future applications and so on. But yeah.
okay, thank you. We have a raised hand, F. Milt. I guess that is Milton Ferreira, maybe?
Yes.
Yes,
Hello.
hello.
Just a curiosity and a question. Why do you need the two-sided operators in your work?
Oh, so try to understand this. Okay. Okay, let's take this picture in here. You are sitting at a point somewhere in here, and you have two boundaries. Now how much effect are you gonna feel is gonna be the summation of one boundary and the other boundary. They put them together will give you the net result. So that's why you need a two-sided operator to have something from the left contribution and something from the right contribution.
Okay. Yes, you want contribution for all the boundary.
All the boundaries, yes. And some of these cases can also be unbounded as well. So, but you'll have to treat it a bit in Unity, how to treat infinite domains, semi-infinite domains. But you get the idea, because because in physics, in nature, things go on disturbance goes on both the direction. It's like I push you, you push me back, and the net effect is that how much I push you minus how much you push me, something like that.
But then you can say that the work of Tarasov is incomplete, or
No, I wouldn't say that. I wouldn't say that. That's a very big statement.
Yes.
That was a brilliant piece of work. But given that there were not many applications, so maybe he didn't consider it. So I wouldn't say incomplete. That's a very big statement.
No,
I'm not in the position to make any.
no,
such.
but in the sense that with one-sided operators, you don't have the contribution from all the boundary.
Pro, pro, Probably the answer is yes. Probably the answer is yes. But one has to also understand what physics is. One is interested in addressing. There may be some physics that's just propagating in one direction. But yes, from two-sided you can go to one-sided all very easy. So the two-sided work is the most general kind. So in that sense, this is much more complete.
Okay, thank you very much.
Yeah, it's like the classical Riemann-Liouville and Caputo derivatives. They're normally done in a one-sided way, and then they're used for time fractional operators where one-sided is fine. And then you have Riesz and fractional Laplacian, which become two-sided.
That was a question? Sorry.
Yes,
Yes.
it's just like a comment to answer Milton's question as well.
Mm-hmm.
Yeah, if you are interested in starting initial problems, okay, that's the approach. But here with boundary, maybe we need these two-sided operators for
Yeah, and
contribution.
Yeah, and realize this two-sided operator is in space, and you also have a time operator which is one-sided. So so the time operator is primarily in one-sided, and the space operators are two-sided, because time is considered to be forward propagating.
Yes. Okay.
So yeah, you have 4 different fractional orders.
Okay, any other questions, comments? All right, then I stop the recording and I think we close the session for today.